Alright, hello, welcome to part 2 of the chapter 4 probability video series. Let's start with this drug testing example. Okay, and I'm going to erase this from before so I have more space to work. Alright, so let's suppose that somehow we know whether someone is using marijuana. Okay, so we have either they use or they don't use. And the testing results, so you give them a drug test. Whoops, you give them a drug test, and the test results can either be positive or negative. Okay, so we looked at total 300 people. And 119 users tested positive. 24 people, they don't use, but they also tested positive. 3 people use, but they tested negative. And 154 people don't use, and they tested negative. This is the rate of, so let me put in here in a different color. This is called the rate of true positives. So these are people who tested positive, and that's true, they do use, they should have tested positive. These are false positives. These people tested positive, but that's false, they don't use. Okay. This is the rate of false negatives. These 3 people tested negative, but that's false. They should not have tested negative, they do use. And these people are true negatives. Okay. So first thing you want to do is put the totals on the table. So calculate the row totals and the column totals. So the 119 and 3, 122, 124, 24 and 154 is 178. And when you add these up, you get 300. Here you get 157. And here you get 143. Okay. And then when you add up these two numbers, you get 300. When you add up these two numbers, you get 300. So your totals, oops. So your totals work both ways. Okay. Now we're going to use this table to answer the following questions. Okay. So in a problem, these 4 pieces of data, 1, 2, 3, 4, 119, 24, 3, and 154 will be given to you, and then you should be able to total that up and fill in the table. So if I choose a person at random, what's the probability of getting someone who had a positive test result? Or, remember this is the symbol for or they use marijuana. So if you remember from before, the addition rule tells us that this is the probability of positive plus the probability of use minus the probability of both. What is the probability of getting a positive test result? That is 119. And this is all out of 300. What is, oh, I'm sorry, that's not 119. So how many people tested positive? 143 total. How many people use marijuana in our sample? 122. and how many do both, meaning they tested positive and they use marijuana. Right here, that's 119. So if you do the math there, you get 146. Okay, and you can convert that to a percent, or you can leave it like that. Okay, let me just convert it to a percent just to see what the percent would be. So that is a 48.7% chance that we choose somebody at random and they either test positive or they use marijuana. This is method 1. You can use this method. There's another way you can do these problems, and that is just to look at the cells in the table. I want the probability of either a positive test result or the fact that they use. How many people tested positive? These two cells, 119 and 24. How many people use? 119 and 3. So I can just add up those cells on the table. 119 plus 24 plus 3. And of course that is always out of the total. Sorry, my handwriting is a little messy. I'm using a new setup on my laptop. It's not that comfortable, but it allows my laptop battery to be charging at the same time while I'm using it. So that's 119 plus 24 plus 3 out of 300, so that still gives me 146 out of 300. Okay? So you'd add up the people who are positive and the people who used and the people who are positive, these 3 cells. Let's look at the next one. What is the probability of choosing a marijuana user? So what's the probability that someone uses marijuana? Let's go up and look at the table. The probability of using is 122 out of 300. Okay. What is the probability of getting someone who had a negative test result or they don't use? I'll just put not use. Again, you can use the addition rule. That's the probability of negative plus the probability of not use minus the probability of both. So negative 157, not use 178. And then the probability of both, not using and getting a negative test result, is right here. The probability of true negative, that's 154. See, that's negative and not use. If you add up all of these, you get 181. You can also use method 2 to add up the totals in the table, or to add up the cells. So I want don't use and negative. That's 3 plus 154 plus 24. And you still get 181. So again, you can use the addition rule, or you can just add up the corresponding cells in the table. What is the probability of getting someone who can pass a drug test? If someone can pass a drug test, that means that they have tested negative. So if you go back to the table and look and see how many people have tested negative, that's 157. Out of 300. And again, you can leave them as fractions or you can turn them to percents. Which events are disjoint? So if you remember from the part 1 video, disjoint or mutually exclusive means that two events cannot occur at the same time. So which two events cannot occur at the same time? Oops. So either they test positive, negative. A person can either test positive or they can test negative. They cannot test both. So positive and negative are disjoint events. And then use and not use. Either someone uses marijuana or they don't use marijuana. You cannot be both a user and a non-user at the same time. Okay? So these two sets of events are disjoint or mutually exclusive. Let me start talking about the multiplication rule, and then I will finish talking about the multiplication rule and move on in part 3. Okay? So let's suppose I have 2 pants, black and khaki, and 6 shirts, red, orange, yellow, green, indigo, and violet. How many different combinations are possible? Okay. Well, I have a pair of black pants, and I have a pair of khaki pants. On the pair of black pants, I can wear these 6 shirts. And on this pair of khaki pants, I can wear 6 shirts. So how many combinations do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So total I have 12 outfits or 12 combinations possible. And I could have gotten that by multiplying 2 pants times 6 shirts. Okay? So with these kind of questions, when they're asking about these different combinations, you can multiply and get the different combinations. What is the probability of wearing a red shirt and black pants? Well, a red shirt and black pants is one outfit. How many different outfits do I have total? 12. So the chance of wearing a red shirt and black pants is 1/12. What is the probability of red and black one day and violet and khaki the next? Alright, so if I wear red and black one day, that's 1/12. And violet and khaki the next. Anytime you see and, you want to multiply. A red and black outfit is one outfit out of 12, and a violet and khaki outfit, that's another outfit out of 12 outfits. So the chance of wearing red and black one day and violet and khaki the next, remember when we multiply fractions, you just multiply straight across, is 1 out of 144. Okay. Here we are choosing the clothes with replacement. That means I'm putting it back. So once I wear that red shirt and black pants, I put it back and it's likely to be chosen again, right? It can be chosen again. So it is with replacement. I'm replacing the clothes and it's possible for me to choose them again. Hence, these events above are independent. What does independent mean? Independent means that the outcome of one does not affect the outcome of the other. Okay? For independent events, we have the multiplication, a kind of multiplication rule. The probability of A and B is the probability of A times the probability of B. And remember that this upside down U stands for and. Okay. You can remember and, whoops, and is like an A, it's like an A without the bar. Okay. So this is the rule for independent events. Okay. Suppose you wear the shirts only once, but not the pants. Okay. So the shirts are chosen without replacement. I wear a shirt once and I'm not replacing it. I'm not putting it back. Now, what is the probability of wearing red and black one day and violet and khaki the next? Okay, so the first day I wear red and black. What's the chance of wearing, how many red shirts do I have? 1. Total out of 6. And then I have black pants, 1 black pants out of 2. So that's still 112. That's what we've seen before, nothing new, right? Now, once I wore that red shirt, I cannot put it back. Remember, the shirts are chosen without replacement. So that shirt goes in the wash. I can't wear that shirt again. So the second day, if I want to wear violet and khaki, what's the chance of that happening? How many violet shirts do I have? 1. Total shirts do I have now? Now I only have 5 shirts because that red shirt is gone. The pants I do put back. So my khaki pants are still 1 out of a total 2. I still have the black pants. So what's the chance of wearing violet and khaki the next day? 1/10. So if I want to look at it overall, what's the chance of wearing red and black the one day and violet and khaki the next? Again, I would multiply. This is a multiplication sign. So that is 1 out of 120. Okay. So this is the chance of the probability of wearing red and black one day and violet and khaki the next day, assuming the shirts are chosen without replacement. Is this larger than the previous case? Yes. 1 out of 120. Oops, my pen is not working. 1 out of 120 is greater than 1 out of 144. Because I have less clothes to choose from, the chance that I'm going to wear any one of those clothes is going to be greater. Okay? When we choose things without replacement, they are not independent, they are dependent. Okay? Let's go back to that drug testing example. Okay? So you have the table for the drug testing example. What's the probability that the first person chosen is positive and the second person chosen is negative? Again, I'm choosing without replacement. That's what WOR means. Without replacement. Okay? So what's the chance of choosing somebody, first person positive, second person negative? Alright, so let me go to my table. Here it is. First person positive, that's 119 out of 300. Okay. Let me just write that on the side here. 119 out of 300, that's the first person positive. Okay. And now I chose that person I examined. Is he positive or negative? He's positive. Okay, then I throw him back in the pile. And what's the chance that the second person... Oh, I'm sorry. I'm making a mistake here. Whoops, scratch that, scratch that. I hope you caught that mistake, huh? The probability that the first person positive is 143. Okay. That's, you pick somebody at random, what's the chance they're positive is 143, because I have total 143 positive results. And then I throw that person back in the pile. What's the chance that the second person is negative? 157 out of 300. And since I want to look at the and situation, first person positive and the second person negative, I'm going to multiply. Again, I apologize for my handwriting. I'm trying to do this while I charge my computer. Okay, so the first person positive and the second person negative is 143 out of 300 times, what was it, 157. Oh, hold on one second. I am sampling without replacement. I think I made a mistake. I am sampling without replacement. Oh, that means I'm not throwing that person back. Oh, scratch that. See, this can be a little tricky. You gotta think about it. Without replacement, that means you're not putting that person back. So I pick one person and he turns out to be 143 out of 300. Probability of positive. So I hold on to that person. Right now I don't throw him back into the pool. Now how many total people do I have now? Now I have 299 people total. Out of those 299 people, how many are negative? 157. Right, so without replacement, you are not replacing them, so you're holding on to them. I hope this is not confusing. We'll do another example just to make this more clear. So that's 157 out of 299. Okay, and whatever number that turns out to be. Let's suppose now I'm looking with replacement. So that means I put that person back. What's the probability of first person being positive, second person being negative? Now we have 143 out of 300. Okay, times 157. I threw that person back. So I still have 300 people total, and out of those 300, 157 tested negative. Okay? So this is with replacement. This is without replacement. Let me look again without replacement. What's the probability that the first person is positive and the second person is positive? So I picked two people at random. What's the chance that they're both positive? Without replacement, I'm not putting them back. So the chance that the first person positive is 143 out of 300 without replacement. So I'm holding on to that person. How many people do I have now total? 299. Out of those 299, how many are positive? 142. See, the first person was positive, so I held on to him, right? Now, the number of positive people I have is 142 out of 299. With replacement. So you're going to throw these people back in the pile. First person positive and second person positive. What's the chance that the first person is positive? 143 out of 300. And what's the chance that the second person is positive? Well, the first person I threw back into the pile. So it's like starting all over again. The chance that the second person is positive now, also 143 out of 300. Okay. So I hope this makes it a little bit more clear what with replacement and without replacement means. I always have to stop and think for a minute. Without replacement. Okay, so I'm not replacing the person, so I'm holding on to them. Okay. And let me stop here, and I'll continue part 3 at this point.